Alright, so we'll discuss electrochemistry in today's lecture. So the topic is broadly electrochemistry and thermodynamics. So as you can see, there are two half cells reactions. In one, there is an oxidation reaction taking place where copper 2 plus is oxidized to copper, and hydrogen ions are reduced to form hydrogen gas. So this is the basic schematic of any electrochemical cells, where we can always divide an electrochemical cell into two parts. The one half is called the reduction reactions, and other half is the oxidation reactions taking place. So divided into two parts, right? So here a potential builds up as a flow of electron. So there is a finite amount of current passing through it. So a potential develops between the cathode and the anode. So this is how the electrochemical cells looks like. It need not to be, it doesn't need to be always look necessarily like two separate cells. This is for your visualization purpose, to understand that these are separate reactions. So we can always separate it out. So hydrogen, this is the reduction reaction, and this is the oxidation reaction. Okay. So in electrochemistry, in EMF, the EMF is of very importance. Is very important in the sense that we need to calculate the EMF of a cell in various situations, and we'll see how to calculate the EMF of the cell based on standard reduction potentials and how it is related to Nernst equation and free energy equations. Okay. So you just have this picture in your mind that there are two separate reactions taking place in two separate cells. In a virtually we can say that one half is a reducing cell, another is the oxidizing cell. Okay. So let's move on to the now the calculation. Now whether the important point is that I can put A, B, C, D, any material. Whether this material will be oxidized, that depends on the reduction potential of that particular material. You might be, you can just all browse through any electrochemistry book, or you can search it online for basic chemistry. I won't go into that detail. So I just outline the major concepts. So that is what is determined by the EMF of the cell, mathematically speaking, right? So theoretically speaking, I will just show you the video. I'll just show you the next slide, sorry, and it will be clear. Let's look at it. Just it's a busy slide. I'll just walk you through it. Don't get confused. There are a lot of concepts punched in, but primarily let's focus on this left, in the left column, in the second row, left column. First column is the first column, second row, right? So in that you can see there are lithium, potassium, calcium, and sodium. These are the very we call it very reacting or very a very active material, in the sense they reacts very quickly with oxygen, with H2O, and they displaces H2 from water, steam, acids, everything. So these are primarily reducing agents, very strong reducing agents. Reducing agents means that they themselves got oxidized in the process of reaction, and they reduce the other element, that is, in case this is hydrogen, right? So these are very strong reducing agents. What does it mean? How it is mathematically how do we express if an element is very is a very highly reducing is a reducing agent, a strong reducing agent? Look at sodium, zinc, calcium, cadmium. These are all alkaline materials, and look at the potential. See, for sodium it is minus 2.71. What does it mean? This is the concept that you need to learn. Otherwise, it's again the same. You can refer any textbook and solve problems. But you have to understand, because I'll be solving 3 or 4 problems which are very conceptually, the conceptual requirements are necessary to understand those problems and solve those. So sodium minus 2.71 means it's very difficult to reduce sodium. It is very difficult to reduce sodium. So it's minus 2.71, minus a high value. It's comparatively easier to reduce zinc with respect to sodium. So in this series if you take any of these, two elements, if you combine any two elements, they will form an electrochemical cell, right? Based on their reduction potentials, one of them will be oxidized and another one will be reduced. For example, sodium clearly seeming to have higher reduction potential than zinc. So sodium will reduce zinc. Okay, sodium will get oxidized itself and will reduce zinc. Again, if I just put zinc with iron, so zinc will reduce iron will get oxidized. So depending on this E0 values, this is called the reduction potential. Reduction potentials are measured, these values are measured against a standard reference electrode, in which case we call it a hydrogen. Look at the hydrogen. See, for hydrogen it is 0. So everything is being measured whether they are able to displace hydrogen. Okay. So we have put a voltmeter. We have arbitrarily said that hydrogen potential for reduction is 0, and based on that, absolute potential cannot be measured. So always we need a reference electrode. So here the hydrogen acts as a reference material. So we arbitrarily set hydrogen at standard pressure, temperature and standard conditions. The hydrogen, for the hydrogen gas evolution reaction, that is H plus 2 electron is to H2 gas, the reduction potential is 0. That is what we mean by this H2 reduction potential 0. Based on the hydrogen, everything has been standardized. So hydrogen is our reference. So sodium, zinc, iron, cadmium, this lead, they are all able to displace hydrogen. Okay, they are able to displace hydrogen from any solution containing hydrogen. What is water? What is it's a acid? So these are strongly reducing agents. But I can also form a cell with sodium and zinc. But higher is the E value. You remember, I will talk about that. Now, if I combine any two material, how are you going to find the EMF of the cell? For example, I combine sodium with let's say copper. I put two solutions together, or I place sodium metal in a solution of copper sulfate, right? So Na2SO4 and copper will be deposited at the anode. So the oxidation reaction takes place at the anode and the reduction reaction takes place at the cathode. Now, if that is the case, if sodium and copper are combined together to form an electrochemical cell, then the EMF will be given by the difference between E right minus E left. Now go to that statement. Go to the first row, first column, small preview. Measurement of a standard reduction potential. It says that M2 plus and M half cell is on the left, and the standard hydrogen cell is on through the salt bridge in the middle. The more active metal M, the greater to H plus, the more negative will be the E cell. So let get into the exact statements. What it means at all is that if you need to calculate the reduction or the EMF of the cell, you need to subtract the right hand side minus the left hand side. At the right hand side, you need to, please remember this very carefully. These are thumb rules, these are conventions, so you have to always follow the convention. At the right, the cathodic reaction will take place. That is basically a reduction reaction. So whenever in an equation, or I'll just show you some problems and I'll divide those problems into half cell reactions, then you can understand what I exactly mean. So one half there is a reduction reaction, one half there is an oxidation reaction. We'll put the E0 value for the reduction reaction at the right, that is the reduction reaction, and the left hand value or the anodic reaction at the left. E cathode minus E anode, basically right minus left means it nothing to do with physically position of the cathode and anode, nothing to do with that. Okay, so higher the positive value of a E cell, stronger will be your potential, or faster will be your reaction, because the potential is higher, the driving force is higher. Higher the E cell value, that is the positive value, higher will be your cell, E cell. So for example, if I include, as we're talking about sodium plus copper, if I combine that, then what will be my net reaction? While it will be my EMF, we can see that the reduction reaction is taking place at Cu2 plus will be reduced to copper. So 0.337 minus of minus 2.71, right? So it will almost come about 3 or 3 point something, right? So it's a positive value. That is, the sodium is being oxidized, so it's a anodic reaction, and copper is being reduced, so it's a cathodic reaction. So the copper will go, the potential, that is the half cell reaction, there is a reference reduction potential. And one thing, remember, everything is expressed in terms of reduction direction, reducing direction. What is the reduction potential? That is, the potential is always measured with its ease to reduce that material. Copper is very easy to reduced, it is easy to reduce copper. That's why the reduction potential is positive. Higher is the reduction potential, positive value, easier to reduce that material. Okay. Similarly, higher the negative value of reduction potential is, they are highly oxidizing agent. They cannot be reduced easily. So they won't get reduced. They will reduce others. They will oxidize themselves. So that is how. Now another concept is, for hydrogen, we also call it as a pH. Please remember, this pH is defined as minus logarithm of hydrogen concentration in your solution. Please remember this. Okay, minus logarithm to the base 10 of hydrogen concentration. So we'll use this concept in somewhere else. So these are primarily the main concepts, and let's move on to the other slide. Okay, so this is I just talked about how hydrogen, and this reduction potentials and everything I talked about, they are all measured with reference to hydrogen. For example, I talked about copper is having a reduction potential of plus 0.337. That means that if I combine copper and hydrogen together with reference to zero potential, that is, which is the hydrogen potential, copper will be having 0.337 volts. The voltmeter will show 0.337. Okay. Similarly, if I combine sodium with respect to hydrogen, the cell reaction will show me minus 2.227. Okay, that's what it means. So if I combine sodium and copper, hydrogen cancels out because there is a reference. So we'll get we'll subtract the E left, E right. We subtract the E left from the E right to get the overall EMF of the cell, right? Okay, I will just solve some problems. Let's move on to another topic. I mean, it's a subchapter, the Nernst equation. So based on, we talked about how to calculate the reduction potential. Now we'll correlate this reduction potential to the free energy. So the first important equation, you should note it down right away, is del G0 equal to minus NFE0. So minus NFE0, del G0, as you know, is a standard Gibbs free energy change for the reaction. Every reaction, being it a electrochemical reaction, covalent reaction, whatever, there is always a free energy change. So the free energy change for an electrochemical reaction is given by minus NFE0, where del G is in joule, N is the number of electrons transferred in that reaction, and E is in the potential. You can also note down the units. Faraday's constant, that is Coulomb per mole electrons, it is 96500. Please remember this value. It will be provided in your gate papers, but you should always remember some standard values. For example, Faraday's constant, 96,500, right? 96500. To be exact, it's 9646, 964640, something else, 96460. But let's forget about that. I'll just 96500 is the Faraday's constant. The other thing you have to determine from the given data and the reaction. So how do you, if I just substitute those reaction, so there is a standard free energy associated to standard EMF of a cell. That is, everything is occurring at a standard state. That is, the activities, you can see the standard reduction of E cell. This Q is 1 for all the species, existing in their standard states. The activities are set to 1, so ln 1 is 0, so that's why you are only left with minus NFE0. In the absence of standard state, you have to take care of the individual concentration and the activities of the material. You have to plug it in the Nernst equation. So your final equation becomes E equal to E0 minus RT by NF ln Q, where ln Q is nothing but the, as we talk about in free energy, it's also a equilibrium constant, and this equilibrium constant is nothing but the ratio between the activities of the product species divided by the activities of the reactant species, or oxidized species by reducing species. You can put it like that as well. So, and always remember, no, that's okay, we'll do it in a proper way. And always remember that everything we are talking about in case of a reduction potential, in terms of reduction potential. This is very important. So these are some equation, and in the last equation, it's being highlighted in yellow. It says that E equal to 0.059 by N log Q, where we have substituted all the constants, leaving only the number of electrons transferred, which is a variable depending on the equation. So if you just put a logarithm to the base 10 in case of and substituting the ln, you will have a 2.303. The R value is constant. Sometimes we say it's 8.314. T is at standard temperature. We call it 298 to 7. That is 25 degrees centigrade. Faraday's constant is 96,500. You substitute everything, you will get a value of 0.059 by N. So 8.314 multiplied by 298 divided by 96,500 will give you 0.059. This is the logarithm base 10. And for 25 degrees centigrade, this is just a substitution, and you'll be needing this equation because sometimes hydrogen concentration is given or the pH values are given. pH values have to be transferred in terms of hydrogen concentration. Okay, so please note it down. These formulas are extremely important for solving the problems. And now we will go into problem solving mode, where we'll take the problem, discuss the concepts and solve it. That will give you the real feel how to solve this electrochemistry problems. Fine. So let's do an easy solution first. Let's do an easy solution first. Please note it down as well, and I am also I just write it down at my board. Please note this down. This question was asked in the year 2007, get metallurgy. Okay, I just write this equation and the relevant equation as well. 2/3 L2O3 plus carbon gives rise to 4/3 aluminium plus CO2. It's in a gaseous phase. The solid, right? And the values are given. 1273 is the temperature, and del G at that temperature 1273 given. Del 0 is a 452 kilojoule. Right? Faraday's constant given. So you need to find out the standard EMF of the cell. Okay. Let's go back to my board work again. Right? I hope you are enjoying this session. Let's solve it. Now I'll just I have talked about a lot about the concepts. Now we'll see how to use those concepts to solve this problem. This is a bit very straightforward. I would say it's an easy problem to solve. Nothing really nothing very complicated here. So what is being done here? This is a standard reduction. It's a thermite reduction. Well, no, sorry, this is a different thing. It's not a thermite reduction. This is an aluminium reduction with carbon at a particular temperature, for which the del G free energy change for this reaction has been given. You need to find the EMF of the cell. So what is your formula? What is your relevant formula? The first thing, the two important formulas in free energy calculation and relating to EMF of the cell is del Z0 is minus NF E0. This is the one equation, very important, that we have discussed, and the one is E, which is not occurring at standard states like del G itself, is E0 minus RT by NF minus RT by NF. 1Q. Okay, these two concepts are very important.